Hi, welcome to this tutorial on the binomial distribution. Now, this is the third one in the series, and in this I'm going to show you how to calculate various probabilities from binomial distributions. Now, I'm assuming that you're familiar what a binomial distribution is and also how to work out the probability of our successes. If not, please go back and look at my first two tutorials. Now, for the first question, we've got a manufacturer of a bag of sweets claims that there is a 90% chance that the bag contains some toffees. And if 20 bags are chosen, what is the probability that 1. All the bags contain toffees, and in part 2, more than 18 bags contain toffees? Now, this particular question is a binomial distribution. Why? Because there are a finite number of trials. There's 20 in this particular problem, each referring to a particular bag of sweets. There are two outcomes in any trial: success, failure. Success being where we pick a bag that has toffees in it. Failure being that the bag does not have toffees. The probability of success remains constant all the way through at 0.9. and the probabilities are independent of one another in any trial. So, typical binomial distribution. But I'm not encouraging you to draw a tree diagram. I just want you to be aware that this is what's going on in the background. Okay, well, let's just remove the tree diagram and we'll get on with the question. Now, the first thing we need to do is to define a random variable. So it can be any letter. I'm going to choose X, and make sure you write a capital letter for a random variable. I'm going to let X be the random variable, and I'll write RV for short. And it's going to represent the number of bags with toffees. Okay, so just write that in. Don't be lazy. Always write a description of what your random variable is going to say if it doesn't say it in the question. And we have to define the distribution that it comes from. So in this case, where X is binomially distributed, remember there's two parameters for the binomial distribution: the number of trials, which is in this case 20 for the sweets, and next is the probability of success. That is, a bag contains toffees, and the probability of that happening is 0.9 for 90%. Now, in the first question, probability that all the bags contain toffees. So for part 1, we're looking for the probability that X equals 20. And assuming that you're familiar then with the formula, it will be 20 C and then the number of successes, which in this case is 20. Then we write down the probability of success, which is 0.9, and this occurs with a success rate of 20, so that's to the power 20, and then you've got 0.1, the probability of failure, and that would occur no times. Next, we need to work this out on the calculator, and you should find that you get 0.12157 and so on, which when rounded comes out at 0.122 to 3 decimal places. So that's a very simple basic question, working out the probability of a particular value. Now, in the next example though, we've got several values because we're being asked the probability that the number of bags that contain toffees is more than 18, so X is more than 18. Now, the random variable X takes on the values 0, because you could find that you've got no bags containing toffees, or 1 bag could contain toffees, 2 bags, and so on, all the way up to 20 bags. So if we're looking for X to be more than 18, it could be that we have 19 bags that contain toffees, or it could be 20 bags that contain toffees, and we'd have to add these two probabilities together. And If we now use the formula for the probability x equals 19, it will be from 20 trials, choose 19 successes. Probability of success is 0.9, and that's repeated 19 times over. Probability of failure is 0.1, and that would only occur once. Then we've got plus the probability of x equals 20, and we could either use the formula again, or we could just simply use the answer we had previously, 0.12157, and so on. And if we add these two values together, what you should find is that you get 0.39174, and so on, which is the same as 0.392 to 3 decimal places, 3 dp. Okay, let's have a look at another question. Now in this question, in clinical trials, a certain drug has an 8% success rate of curing a known disease. And if 15 people are known to have the disease, what is the probability that at least 2 are cured? Now, this again is a typical tree diagram. We've got a finite number of trials, 15. There's 2 outcomes in any trial, that is that the drug is successful or it fails. The probability of success is 8%, and it remains constant throughout the problem. And in any trial, the probabilities of success are independent of the previous trial. So a typical binomial distribution. So, first of all, to do this, let us define a random variable. It can be any letter, remember. Why don't we choose y? Okay, let y be the random variable in this particular problem, and it'll be the number of people cured. So we've defined that, and we now need to say where y is distributed binomially. 2 parameters, number of trials first, which is 15, and the probability of success next, which is 8% or 0.08. So in this particular question, we're asked that the probability that at least 2 are cured. So that's the probability that y is greater than or equal to 2. Now in this particular problem, y can be no people being cured, or 1 person being cured, 2 people, 3, 4, etc., all the way up to and including 15. So this is the same as the probability that y equals 2 plus the probability that y equals 3, y equals 4, and so on, all the way up to the probability that y equals 15. Now this would be a horrendous sum to work out. And there is a way around this problem. What we should know is that if we were to work out the probability that y equals 0 plus the probability y equals 1 plus the probability y equals 2, 3 and so on all the way up to 15, that would total 1. All the probabilities would total 1. So since I'm not using y equals 0 and y equals 1, I could take those probabilities away from 1 and it would give me this answer. So I could do 1 minus the probability that y equals 0, and I'd need to put this in a bracket, plus the probability that y equals 1. These are the only other situations that I've not included here. So all I need to do now is just work out these two rather than having to do all this lot. So it'd be 1 minus, so for the probability y equals 0, it would be 15 C 0. Probability of success is 0.08, and that is occurring no times. Probability of failure is 0.92, and if we had no successes, there must have been 15 failures. Now we work out the probability of y equals 1, so that'd be plus 15 C1. Probability of success 0.08, would have occurred just once, and the probability of failure would have occurred 14 times. So we have 0.92 to the power 14. And if I leave it to you to work this sum out, remember I must put that in brackets by the way, if I leave it to you to work that sum out, you should find that you get 1 minus 0.6597 and so on. And if you take that away from 1, you end up with 0.34027 and so on, which when rounded to, say, 3 decimal places is 0.340 to 3 decimal places. Now that brings us to the end of this tutorial, and I hope you've been able to follow these examples and you can apply them in similar questions. Now in my next tutorial, what I want to show you though is how on some occasions we can do questions like this by using cumulative binomial distribution tables, and that can save us an awful lot of work. So I hope you'll have a look at that tutorial.